found motor tanker called the Brer, laden with 84,000 tons of Gullfaks crude oil, was on passage from Mongstad, Norway. She was bound south of Shetland through the Fair Isle Channel for Canada. The vessel was suffering typical January weather in the North Sea when she suffered complete engine failure. The wind at the time was very strong, making the Shetland Islands a lee shore. Despite efforts by salvage teams and coastguards, the vessel was driven ashore on Samborough Head and was a total loss. All crew were rescued, but it was a great environmental disaster, resulting in the loss of vessel and cargo. The main cause of the disaster was heavy weather conditions. The learning objectives of this chapter are that you will be able to demonstrate knowledge of the meteorological systems producing wind with associated wind strengths, the location of temperate latitude depressions and winds associated with them, how fully developed sea waves are produced with associated wave heights for wind strengths on the Beaufort wind scale, the location of storms and the seasonal aspects of some weather systems causing storms, the construction of a tropical storm with dangerous and navigable semicircles, localized winds producing heavy weather effects. A basic definition of heavy weather is that the wind is at least Beaufort Force 7, with a wave height of 4 meters or more. In reality, there are other factors that determine if a vessel is in heavy weather. A more realistic definition is to say that if a vessel or her cargo is seriously affected by environmental conditions caused by a meteorological system, it is in heavy weather. In heavy weather, the intense atmospheric conditions and large environmental forces make navigation difficult. There is the added risk of damage to the vessel and cargo and injury to the crew. Defining heavy weather using wind force alone is not always relevant because of the different types of vessels found at sea. What is heavy weather to one vessel might not affect another. A good example of this is a large vessel boarding a pilot from a boat in blustery conditions. The large vessel is hardly affected by the weather, but the pilot cutter is suffering in wind and relatively big waves. A common link with all vessels is the presence of crew on board who are always subject to the effects of heavy weather on their vessel. The illustration shows increasing and decreasing buoyancy force on a vessel which causes movement in waves. A very important factor also affecting vessel motion is the wave length relative to the vessel's length or beam. When the wavelength is about twice the vessel length, it will pitch. When the wavelength is about twice the vessel beam, it will roll. Vessel motion is caused by the increasing and decreasing buoyancy forces acting on the vessel's hull. The illustration shows that a large vessel sometimes plows into waves that a smaller vessel will ride over. The large vessel is therefore more vulnerable to damage with water breaking over it. This can happen in any part of the vessel, but is most likely in the bow area when ploughing into head seas. The smaller vessel riding over the same waves will, however, suffer more violent vertical motions than the large vessel. A heavy, laden vessel with a full-form hull, such as a bulk carrier, meeting head waves, risks ploughing into them rather than rising above them. This can cause water to hit the forepart of the vessel hard, risking damage. Whereas a vessel with a fine hull and bow section is more likely to cut through a wave, but then has a worse potential for water on deck, as there is less buoyancy forward to make the vessel rise over the wave. The illustration shows that the shape of the hull dictates how the vessel responds to waves. The naval vessel, with fine bow section but no bow flare, cuts through head waves and is able to maintain high speed. There is often a breakwater fitted to shed any part of the wave coming on deck. The container vessel also has a fine bow section and is able to maintain high speed in head waves. However, unlike the naval vessel, it has a pronounced bow flare, which causes the bow to lift, preventing water coming on deck. Unfortunately, as we shall see later, vessels with a fine bow section and flare suffer unwanted rolling effects in heavy weather. Some vessels have a much larger surface area in light ship condition compared to when fully laden. The force on a vessel due to wind is proportional to the area of the exposed hull and accommodation. It follows that for these vessels, wind force must be greater when light than when laden. Other types of vessels illustrated hardly change their exposed surface area with their condition of loading. The illustration shows two air masses coming together with warmer, less dense air rising above the colder air. The process drags in air from the surroundings, producing surface wind, the direction of which is modified by the Earth's rotation. The strength of the wind depends upon the intensity of convection, with a more intense convection producing a stronger wind. A center with low atmospheric pressure develops, called a. Over the sea, warm, moist air is drawn into the center, taking moisture into the atmosphere and causing clouds to form. Areas not covered by cyclones have anticyclones, which are high-pressure areas resulting from the presence of heavier, colder air. The illustration shows a weather map with pressure systems on it. Other names for a cyclone could be a low-pressure center, low or temperate latitude depression. Another name for an anticyclone is a high-pressure center, or simply a high. Air drawn into a cyclone starts to rotate around the center of low pressure in an anti-clockwise direction in the northern hemisphere, clockwise in the southern hemisphere. The greater the pressure gradient between the center of low pressure and the surrounding air, the stronger is the generated wind. The strongest winds are often found behind the cold front. In tropical latitudes, a cyclone can become very intense because there is an abundance of warm, moist air to fuel it. Observance of the barograph trace can reveal an unexpected drop in atmospheric pressure, called a baroclinic wave that can signal a developing tropical cyclone. Ballard's law can be used to locate a low-pressure center. The illustrations show that in the northern hemisphere, stand with your back to the wind, and the low-pressure center lies to your left. In the southern hemisphere, the low pressure lies to your right. Very strong winds can develop when a temperate latitude depression pushes up against an area of high pressure. The large pressure gradient between the two systems increases wind strength. The illustration shows lines of equal pressure, called isobars, very close together. This is a good indication of strong wind in that area. Temperate latitude cyclones occur in any part of the world between the latitudes of 30 and 70 degrees. Tropical cyclones occupying latitudes between 30 degrees north and south. Cyclones track across oceans, reducing in intensity when they cross land, but never cross the equator or intertropical convergence zone, ITCZ. When a tropical cyclone has great intensity, it is called a tropical revolving storm. A sea temperature of 26 degrees Celsius or above is needed to create an intense tropical cyclone. Temperate latitude depressions or cyclones have wind strengths associated with them that lie somewhere on the Beaufort scale, rarely reaching hurricane force. Click the slider to each Beaufort scale to see the corresponding wind speed and average wave height for well-developed waves. Very damaging conditions occur when heavy weather interacts with other physical features, such as currents and the seafloor. The illustration shows the southeast coast of South Africa, which is one of the areas associated with heavy weather conditions. Let's try an activity to identify areas with tropical revolving storms. Click the numbered hotspots on the world map to identify areas associated with tropical revolving storms. Hurricanes are found in the Atlantic Ocean from West Africa to the Caribbean. Cyclones are found in the Indian Ocean. Some head north into the Arabian Sea. Hurricanes are found in the eastern Pacific, from mid-Pacific to the coast of California. The most common place for a TRS in the world is the western Pacific, from mid-Pacific across to the Philippines and coasts of Japan and China, where they are called typhoons. Hurricanes are found very occasionally or rarely on the northeast coast of South America. Cyclones are found from northwest Australia across to Madagascar and southeast Africa. The local name for a TRS is a willy-willy around Australia. Hurricanes are rare in the eastern Pacific Ocean. Typhoons move from mid-Pacific towards Indonesia and the northeast coast of Australia. The animations show the dangerous and navigable semicircles for a In the northern hemisphere, wind rotates in an anti-clockwise direction around the low-pressure center of the eye of the storm. There are dangerous and navigable semicircles defined relative to the direction the TRS is traveling. In the dangerous semicircle, wind speeds are greater due to the speed of the storm adding to the cyclonic wind speed. In the southern hemisphere, wind rotates in a clockwise direction around the low-pressure center of the eye of the storm. There are dangerous and navigable semicircles defined relative to the direction the TRS is traveling. In the navigable semicircle, wind speeds are smaller due to the speed of the storm subtracting from the cyclonic wind speed. There are different wind classifications for tropical revolving storms. Click on the countries to see how each one classifies them. There are areas in the world where storms, and hence heavy weather conditions, are seasonal. Click on each type of weather system to view more information about its seasonal effects on heavy weather.